All right, today we are diving headfirst into one of the biggest puzzles in all of cosmology. Seriously, it's a cosmic mystery that has scientists pretty much stumped. So let's get right into it. Okay, so it all boils down to what sounds like a simple question, right? We know the universe is expanding, but just how fast is it going? And trust me, getting this number right is absolutely crucial. It affects, well, everything we think we know about our cosmos, from the Big Bang all the way to its ultimate fate. And this is where the plot thickens. Because when scientists try to answer that one simple question, they get two different answers. And we're not talking a little bit different. No, these answers are fundamentally, frustratingly different. And that, right there, is a massive problem. You know, it's one of the most basic ideas in physics. No matter how you measure something, you should get the same answer. It's just common sense. But when it comes to the expansion rate of our universe, our very best measurements are giving us this huge, glaring contradiction. Let me put it this way. Imagine you're measuring a room. You use two different tape measures, and you trust them both. But one says the room is 10 feet wide, and the other one says it's 12. I mean, both can't be right, can they? Well, that's exactly the situation cosmologists are in right now. So, okay, if we're gonna solve this thing, we have to look at the evidence, right? And in our little cosmic detective story here, that means we need to examine the two main methods scientists are using. These are our conflicting clues. So, on one side, you've got measurements from what we call the local universe, things that are relatively close to us in the grand scheme of things. And then on the other side, you have measurements from the primordial universe. We're talking about the oldest light you can possibly see. Two totally different ways of looking at things that, in a perfect world, should give us the exact same answer. All right, so let's look at that first method. This one focuses on things that are, in our cosmic neighborhood. The key here is using these incredible exploding stars called supernovae. The thing about them is they are so unbelievably bright, and their brightness is so predictable that scientists can use them as standard candles. It's like knowing the wattage of a light bulb. If you know how bright it truly is, you can figure out how far away it is. It's a fantastic way to measure huge cosmic distances. And when they crunch all the numbers from those supernovae, they get this. 73. Now that's 73 kilometers per second per megaparsec. And just so you know, a megaparsec is just a crazy huge unit of distance, about 3.3 million light years. So basically, for every 3.3 million light years you go out, the universe is expanding 73 kilometers per second faster. Got it? The key number here is 73. Lock that one in. Okay, now for method number 2. This one is completely different. It looks all the way back in time. We're talking about the literal afterglow of the Big Bang. It's called the cosmic microwave background. By studying this ancient light, scientists can build a model of the baby universe and basically calculate how fast it should be expanding today based on those early conditions. And the number they get from that, 68. Wait, what? Not 73, 68. And that is a huge difference. It's way, way outside any possible margin of error. So let that sink in. The two most reliable methods we have are giving us two completely different answers about our universe. This whole problem has a name, and it's a big one, the Hubble tension. Some people even call it the crisis in cosmology. And that's because it's not just a small error. It suggests that something might be fundamentally wrong with how we understand the entire universe. It might even mean we need brand new physics to figure it all out. But just recently, a new cosmic detective has entered the scene. Actually, two independent teams of researchers, and they decided to tackle this problem from a totally different angle, using a brand new method to see if they could finally crack this case. So instead of looking at those faraway supernovae or that ancient light, they focused on galaxy groups right here in our backyard. See, in these groups, you have this constant cosmic tug-of-war happening. You've got gravity pulling all the galaxies together, but at the same time, the expansion of the universe is trying to push them all apart. So here's how they did it. First, they looked at nearby galaxy groups, like the one around the M81 galaxy. Second, they carefully analyzed that push and pull, that balance between gravity and expansion. And third, and this is the really important part, they used a different kind of cosmic ruler. Forget supernova. They used a specific type of star called a red giant. And at the very tip of their brightness, they have a really predictable peak, which makes them another amazing tool for measuring cosmic distances. So you've got this totally independent method, right? Using different data, different stars, a whole different approach. It promised a fresh pair of eyes on the problem. And what they found? Well, it might just be the break in the case that cosmologists have been desperately looking for. So, what number did they come up with? Around 64. 64 kilometers per second per megaparsec. Okay, now let's take that new clue and see how it fits in with our other suspects. Okay, let's line them all up. You have the number from the local universe using supernova way up at 73. Then you have the number from the early universe, the cosmic microwave background, at 68. And now, this new independent measurement from galaxy groups is down at 64. Well, look at that. It is clearly much, much closer to that early universe number than it is to the supernova number. So what on earth does this all mean? What does this new piece of evidence tell us about the whole mystery? Well, the implications are actually pretty profound. This could seriously reshape how we see the entire cosmos. So here are the big takeaways. First, if this new number is right, the Hubble tension gets a whole lot smaller. That huge gap between the high and low numbers starts to close. Second, it could mean we don't actually need to invent some kind of new physics to explain everything. Maybe our current model is okay after all. And third, and this one is a bit of a curveball, it suggests something really surprising about dark matter. See, the old way of thinking was that these galaxy groups are just dominated by these massive, invisible halos of dark matter. But this new data? It suggests that the bright, shiny galaxies we can actually see, like M81, contain most of the mass. The gravity seems to work out without needing nearly as much dark matter as we once thought. So, does this mean the case is closed? Have we solved the Hubble tension? Well, it's a giant leap forward for sure, but the case isn't quite closed yet. We still need more data. But it leaves us with this incredible question. Are we finally zeroing in on the real expansion rate of our universe? Or is this cosmic mystery just getting started?